Hello, Triple E 470. My name is Jared Blunt, and I am a classmate of yours in this power system analysis class. And I work for Southern California Edison as a supervising test technician. And I find myself in a position to give you a virtual tour of a substation today. So I thought I'd take advantage of it, and hopefully this might help clarify exactly what kind of components are in a substation, and just to give you a kind of a high-level view of what we have here. So I'll do my very best. I don't make very many videos, so hopefully this isn't too bad, but hopefully this might answer some questions for you as far as what exactly is in a substation. So we'll start off by the lines coming in. So the voltages for this substation, or what we call a 66 to 12 kV substation. So you have two lines that are coming in, okay, and then dropping over here to these two circuit breakers. Okay, those are 66 kV circuit breakers, and then those come over, feed what we call the operating bus. Okay, and then that current will flow through the transformer bank circuit breaker, go through the transformer that is over there, and we'll get a closer look at that later, and then to the 12 kV side of the substation, which we'll take a closer look at as well, out to all the lines, the distribution lines that feed electricity to our customers. So starting off with 66 kV components, and I apologize for any shaky cameras. Like I said, I don't do many videos, but you have your 66 kV line coming in, okay, and they come down, and they come over here to the 66, what we call line disconnects right here. Okay, so any type of major piece of equipment in a substation, you're going to have disconnects on both sides. Okay, so those would be the line disconnects for this CB right here, and then you'd have the bus disconnects for the operating bus. So any circuit breaker that you come across, there's always going to be two sets, or at least there should be two sets of disconnects, so that you can isolate that circuit breaker, remove it, repair it, otherwise it'd be live all the time, and there's nothing you would be able to do to the circuit breaker. So right there, let's see if I can get it back. There it is. That is the line pot. So this is a transformer that's measuring the voltage of that incoming line, and why we use that to determine if that line is actually energized or de-energized. So if the line is energized, right, there's going to be voltage going across that line transformer, and that'll send a voltage signal to our monitoring equipment inside to tell us that we have a hot line. If the line is de-energized, then there will be no voltage potential across that transformer, and that means there will be 0 volts going into our monitoring equipment, and it'll tell us that we have a dead line. Okay, coming over here, this right here is a 66 kV breaker. Okay, it's a SF6 breaker. So SF6 standing for sulfur hexafluoride. Okay, as you can see, those main contacts for the breaker are inside those barrels. SF6 is serving as the dielectric, and without it, that 66 kV potential would definitely flash over, because if you notice, like, I can walk up to this breaker right now and touch it. Okay, I can do that, and the reason I can do that is because this equipment is grounded. It's mounted through the steel lattice and grounded to the station ground. If that SF6 wasn't there and that ground wasn't there, I would have died just then when I touched that breaker, because there would have been so much potential there that if there was a path to ground through me, it would have definitely flashed over and through me. But that isn't the case because we have SF6 and it's properly grounded to the station ground that's underneath. So inside this breaker, I should give you a little quick tour inside. So right here is the what we call the CB mechanism. It's what actually opens and closes the breaker. Okay, and then there's a whole bunch of knife switches and fuses and CT rotos and all those wires coming right there. Those are the CT blocks, which all those leads are coming from the CTs that are inside those cans. So as we're looking at this breaker, okay, that lead comes in, right? You got your high side, you got your bushings on this side and bushings on that side. And inside those cans are the current transformers, and those are the devices that measure the current flow through the breaker. For those who are interested in protection, one of the basic tenets of protection when it comes to circuit breakers is that the protection always looks through the circuit breaker, okay? Always through the circuit breaker. So it's gonna go, if we're looking at current coming from the line, it's gonna come down, okay? Through the line disconnects, down, through the bushing, current coming through the CTs, across the breaker, up this way, and then down and over to the operating bus, because the line is feeding the operating bus. Okay, so always remember that the CTs look across the breaker when it comes to protection. So these CTs right here, okay, that are looking across the breaker and going over are protecting the operating bus, those three lines right there. Okay, these CTs right here are looking across the breaker, back up through, or excuse me, through the CT, through the breaker, and to the line. Okay, so those CTs right here are watching the line. Those CTs here are watching the bus. Okay, same thing here. Okay, so this is another line breaker. So these CTs going through the breaker to the bus. These CTs looking through the breaker off to the line. So all these 66 kV breakers are, I mean, built the same. It's just how you use them, and so, you know, those two are being used for isolating the lines and the bus. Excuse me. This breaker is being used to monitor the transformer bank. Okay. This breaker, what we call the bus tie, is being used to, it's basically a spare breaker that allows us, if we need to take a CB out for maintenance, allows us to use this breaker to either have line, to allow a line to come in, or to use this breaker to feed the transformer bank if we had to do maintenance on the bank breaker. Off to the distance here, that is those are shunt capacitors for the 66 kV bus. Okay, so if you notice, here's the operating bus. There's lines that go down to those big cables, and then it runs underground, and those big cables come back up. And then you have your capacitor breaker there, which energizes 66 kV capacitors, and you use that for voltage support. So if there's a lot of load and it wants to pull down the voltage, they can close that breaker in, energize those capacitors, and it'll supply reactive load, which will raise voltage. Okay, so you saw capacitors in the textbook and your drawings. Well, there they are, and that's what they do. And there's a set for each phase. You got 3 wires coming in, set for each phase. So back to the bank breaker, right? So in this case, right, the bus is feeding the bank, so power flow would come through these bus disconnects, okay, down through that CT, through the breaker, up through that, up through the CTs and the bushing there, over, up through the bank disconnects, and over and down to the #1 bank. We're gonna walk over there. So this is our transformer bank, And you can see that those leads come down, right? This transformer is going to have two sides. It's going to have 66 kV side, 12 kV side. Okay, so you can see those bushings that have oil sight glasses. Those bushings are full of oil. So you got those bushings that are the 66 kV bushings, and then when we were talking about lightning arresters, there they are. You see that lead that comes over and down to those 3 lightning arresters, and their whole purpose in life is to prevent an over voltage condition inside that bank. So if a lightning strike hits, or there's some sort of transient on the system that makes voltage go real high, it'll actually flash over through that lightning arrestor to that ground wire and probably destroy the lightning arrestor in the process. But we would much rather destroy a lightning arrestor than have that same transient get inside the bank to where the windings are and have the flashover happen there, because it's a lot easier to change out a lightning arrestor than it is windings inside the bank, that's for sure. And then of course what you see here, that is a fan bank that's helping keep the transformer cool. So I'm walking over here, I'm going to show you the nameplate of the transformer. So as you can see, okay, this transformer has a nameplate. There's your MVA ratings at different temperature rises, high and low voltage ratings, your impedance based on the lowest MVA rating, the cooling class. So this is a oil to air, oil to air, and then 2 sets of fans. Excuse me. And based on your cooling class and what you have available, if all you have is oil to air, let's say both of your fan banks are down, then depending on your temperature rise, okay, you're rated for 15 or 16.8 MVA. And that's it. That's all the transformer can handle if all you have to cool the transformer with is just heat transfer across the transformer casing to air. But if you have both of your fans available, okay, now your rating is up to 25 for a 55 C rise and 28 MVA for a 65 degree rise. Okay, here you see what we call the vector diagram. Okay, so if you look, you got H1, H2, H3 there, X1, X2, X3, and then your neutral connection there. If you look at this little dotted line, that's called your origin vector, and it's pointing towards H1. So imagine, if you will, a clock, and pretend that that's your 12 o'clock position right there. Okay, what you would do is you would find the X1 on the other side, okay, and then compare that origin vector to this vector, okay, in its direction. So if we were to put this on a clock, and if we were to take that vector and transpose it over here, so imagine, if you will, a dotted line from there to there, if that was 12 o'clock, then X1 is 30 degrees to the right, which would make that 1 o'clock. So in that case, you would have what would be called a DYN1 transformer. Capital D for the high side of a delta, little y because the low side's a y, okay, the little n because you have a neutral connection, and 1 o'clock because you have X1 would be at a relative position to H1, this origin vector, 1 o'clock. So D, big D, little y, little n, 1. And then you see the actual transformer connections, your H1, H2, H3 bushings, okay, and your low side bushings here. And then where all the connections are internal. So you have a de-energized tap changer that you can utilize there, which I'll show you in a minute. Okay, and if you look at the vector diagram, if I look from H1 to H3, okay, that should be in phase with X1 to X0. So here's X1 and X0, okay, so that's going up here, through here, down this way. Well, that should be in phase with H1 to H3. So here's H1 coming down, going through the high side, over to H3. Okay, if we went H2 to H1, that should be in phase with X2 to X0. So H2 comes down over to H1, X2 coming up over to X1, and the same thing for H3 to H2 would be in phase with X3 to X0. Okay, so that's how a vector diagram works on these transformer nameplates. If you look down here, got your low voltage connections. There's only one connection. All right, this is a B bank. It's not a big 280 MVA bank with a low tap changer, so there's no low tap changer, so there's only one connection. Okay, and it tells you if you're rated for 28 MVA, your max amperage through this bank is 1296. That's your 100% load. Can the bank handle more? Yes, but based on who's operating the transformer, there's guidelines on how much you should overload a bank and what, if you should, how you should. If if there's an emergency, you can overload it. But temperature control of a bank is very important, and current going through a bank is what's going to generate your heat. And you can get to a point on transformers where if you overload them too much, that they will do what's called runaway. And if a transformer runs away, then it's done. It's going to burn up. There's nothing you can do to cool it back down. It just gets to a certain point, and it'll just keep excuse me, it'll just keep getting hotter, and there's nothing you can do about it. So you want to avoid that. Here on the low side, you have your high voltage connections, and if you notice, okay, you got your voltage here. There's 5 different voltages, okay, and there's 5 different tap changer positions. And on these, this is what's called a de-energized tap changer. So in order to go from A to B, B to C, and change the connections, you have to de-energize the transformer. You have to turn it off, okay? So in fact, I'll show you the handle a little bit. There's even a lock on there to prevent you from operating that tap changer while the bank is loaded up. Okay, so if you notice with these taps, A, B, C, D, and E, it shows you what connections are being made. So if you look in really close, I'll let that focus in. Hopefully it'll focus. Maybe it'll focus. I don't know if it's going to focus. Okay. Well, hopefully you can see this somewhat decently, but if you can't, right, 11 and 12, right, so that tap changer would connect 11 with 12, which would give you the full coil, okay? The next tap down would connect 12 and 13, which would take out a few of these coils, okay, or turns, right? 13 to 14, right, takes out a few more turns. 14 to 15, a few more. 15 to 16, a few more. Every time you take out a few turns, you're changing that turns ratio, which affects, the transformation of voltage through the bank. So that's why these tap changers are here. So, because at least here in California, in Central California, you get hot. There's the summer, which is really hot, and winter is really cold. So the summer's really hot, we have to change the taps in order to maintain voltage control, because we're going to be feeding more load. And then in the winter time, that load goes down because it's cooler, right? And so we have to readjust our tap, right, to maintain the voltage that we want to maintain going through the station. Here you can see the capillary temperature monitors here for both the oil temperature, the liquid, and then the hot spot. And if you notice those little silver things up there, okay, those are set points for bringing in temperature alarms if the bank gets too hot. Okay, and then you have a white needle, which gives you what the current temperature is, and you have a red one, and that red one tells you the highest it's been since you've checked it last or reset that needle. So the highest it's been is pretty close right there. It's been, it looks like about 50 degrees C, and that probably happened on the hottest day of the summer is when it got there. Okay. Okay, so we were talking about the de-energized tap changer and how you do not want to change the taps under load. And you can see there's a lock on there, and it says caution, de-energized transformer before operating tap changer. So there you go. I mean, if you operate it and it's under load with a lock and that warning on, then you're either did it deliberately, or you're just stupid enough where you shouldn't even be in a substation in the first place. So yeah, do not change the de-energized tap changer while the bank is under load, or even energized for that matter. Turn it off. Can't stress that enough. All right, so now I'm going to take you through the low side of the bank. So same thing, you see the smaller bushings, and you got the lightning arresters, which are smaller too. But if you notice, look at the size of the leads, right? You got your 66 kV leads are coming in, okay? Then you got your 12 kV leads coming out, and they're bigger. And they're bigger because there's more current on this side of the bank. And so you need bigger conductor to handle that current. All right, so you got the current coming off, going up and over. And it goes to that number one 12 kV bank. And then from that 12 kV bank, we'll get a little closer look at the breaker here. All right, those leads come in, come down through the circuit breaker, same thing, right? Okay, you got CTs checking both sides, coming up through this jack bus across the bank disconnects here and up to this operating bus. We got these big three pipe looking things. That's our operating bus on the 12 kV. And then here you got all the breakers that are feeding all the different lines. Okay, all the same type of breaker, they're just doing a different job. So those breakers, current going through, comes off, and it's going to these underground getaways that are popping up over there on the pole, over here and over there. Okay, that's our transfer bus, okay, in case you needed to use the bus tie. And then right here, these three pots right here, that's monitoring the 12 kV bus voltage. Now I'll take you to get a quick look. Okay, as we had caps on the 66 kV side, we also have caps on the 12 kV side. So there's the cap breaker, set of 12 kV caps doing the same thing, right? Energizing them, they'll start producing reactive load, okay, in order to bring up bus voltage if we have a lot of load on the bus. That's their purpose there, just the same as it is on the 66 kV side. So that's the outside of the sub, and I'm going to go ahead and pause this, and I'll take you inside the control room real quick so I can show you what the relays look like. Alright, so we're here in the control room, okay, and these are relay racks, and these are microprocessor relays that are looking at, depending on what they're looking at, voltage and current, or just current, to protect lines, banks, other pieces of equipment in the system. So, you know, for example, you know, we got two relays here. One's a GE relay, right there, that's a GE relay, and the other one's the Schweitzer. Okay, and they're what's called a D60 and 311C, which are distance relays. And so they're looking at conditions on the line, okay, monitoring the current, and they're also monitoring which direction the power is going, if it's flowing into the station or from the station out to the line. So if you are once again interested in protection, remember that when it comes to protection, okay, you want speed, okay, you want accuracy, but you also want selectivity. So if the station is not feeding the line, if there's a fault, let's say on this line that these relays are monitoring, but the fault is not being fed from the station to that fault, then we don't want these relays to operate. Okay, that's part of the selectivity requirement for protection. But if power for some reason was coming from the station and this station was feeding a fault, then these relays, we would want them to operate and open up the breaker and help clear the trip. Okay. Here are bank relays right here. Okay, so you see one that says F35, one that says T60. Okay, so the F35 is what we consider the high side overcurrent. Okay, so it's looking at all it's looking at is current, and the sudden pressure element is also going through this relay as well. So if there's a sudden pressure or a high or a overload, then this relay will trip the bank breaker and de-energize the bank. The T60 is a transformer differential relay, and so it's looking at the currents coming into the transformer, and it's looking at the currents coming out of the transformer. And with transformers, even non-ideal ones, I mean, they're still fairly accurate, or no, excuse me, not accurate. They're still pretty efficient, and you know, the apparent power going into a transformer needs to equal the apparent power coming out of the transformer. And if it doesn't, okay, then there's a problem. There's a fault or a situation inside that zone of protection between the high side bank breaker and the low side bank breaker that requires you to trip the bank. Okay, so remember that this differential is all about power in equals power out. Always, always, always. What goes in must come out. Okay. Without getting my guys in the shot, I was just going to show you these three relays really quick. So those are all, okay, GE relays, monitoring lines. Okay, that's bus differential relay there. Okay, when we're testing a relay, that's what it looks like there. We're testing. My guys are really trying not to be in the shot, and I'm not going to put them in the shot. So that's a 12. We're testing this 12 kV relay right now. Actually, just changing the reclosing settings, and that's what our power system simulator looks like going in there. And with any substation, you're going to have a battery bank, okay, and you're going to have AC and DC loads. And then last but not least, okay, you're going to have, at least this substation has an HMI, okay, where you get a one-line representation of the station telling you the status of breakers and currents, and gives you any alarms that may come in due to abnormal situations in the sub. So that's it. That's just kind of a high-level overview of a substation tour. If you have any questions, be more than happy to ask. If there's anything you'd like to see, feel free to shoot me a response or a question, and I'll answer it the best I can. Some things I probably won't be able to show because of NERC SIP, especially on the higher voltage stuff, but I think this tour of a B station gives you a general good overview of the flow through a substation and a lot of the major components that are inside the substation. So thanks for your attention on this, and hopefully I wasn't too bad. Bye.